Okay, in this video we're going to talk about the degree of a graph and the degree of the vertices in a graph. So we call the degree of a vertex, which is denoted degree of V, the degree of a vertex V, is equals the number of edges incident on V, where a loop counts as two edges. Okay, so in this graph illustration here, if we look at vertex V1, it's kind of a nice way of doing this is to imagine that you have a little circle around V1 and how many lines are coming out of that circle. Well, there's 3 of them, so the degree of V1 is going to be 3. Now if we look at V2, this is where a lot of people get confused, but again, we have a little circle like that, and there's 3 edges coming out of it. Even though 2 of them are from a loop, as we said in our definition, a loop counts as 2 edges. Well, this is one explanation of why. You just have to make that little circle small enough. And here we only have 2 edges coming out, so V3 has degree 2, which means the total degree of our graph is going to be 8. So this is an interesting question. We're told that we have a graph that has vertices of degrees 0, 2, 2, 3, and 9, but we're not given the graph itself. From this information, we want to figure out how many edges does the graph have. Well, a great place to start on this is to figure out how the degree of a graph relates to its number of edges. So first, we want to think about how many degrees each edge adds to the graph, right? So if we have an edge, and it's 2 endpoints, V1 and V2, how many degrees does that add? Well, I don't know how many other edges are attached to V1, for example, but if we draw that circle that I mentioned on the previous slide, we can see that our edge of interest, this one between V1 and V2, is going to add 1 degree to the degree of V1 and 1 degree to the degree of V2. So each edge then contributes 2 degrees to the graph. 1 for each endpoint. And this also helps explain why loops contribute degree 2, right? It's 1 for each end of the edge. Well, what does that mean? That means that the degree of the edge should be twice the number, the degree of the graph should be twice the number of edges, right? Since each edge contributes 2, the degree will be twice the edges. So we have the degree of a graph, G, is equal to twice the number of edges in G. Well, that's interesting, because that means the total degree of a graph is always even. Okay, so looking at our problem, the total degree of our graph which we don't know what the graph is, but we're given in the problem, is 0 plus 2 plus 2 plus 3 plus 9, and that is going to equal 16. And so the degree of our graph G is equal to 16, which is equal to 2 times the number of edges in G, which means that the number of edges in G is equal to 8. So there are 8 edges in the graph. This next problem, I'm going to challenge you to pause the video and try to draw a graph with 4 vertices that have degrees 1, 1, 4, and 2. Okay, I hope you tried to do that on your own. Let's see some examples of how this can be done. So there's actually many different ways to do this. I'm going to show you, here's 3 ways that I've seen people do it before. Let's look at this first one. We have degrees 1, 1, 2, and 4, which is exactly what we want. 1, 1, 2, and 4, 1, 1, 4, and 2. Here we have 1, 1, 2, and 4. Here we have 1, 1, 2, and 4. So this task can be completed in many different ways. There are many graphs that have this this property. Okay, this is a little bit more challenging. I want you now to draw a simple graph with 4 degrees, 4 vertices of degrees 1, 1, 4, and 2. So this is the same problem here, but notice in each one of these solutions, the graph is not simple. There's either loops or parallel edges. So why don't you pause the video and spend a few minutes trying to draw a simple graph with 4 vertices of degree 1, 1, 4, and 2. Now, if you've spent a while trying, you may have noticed this is really hard. In fact, you're not going to be able to do it. This graph does not exist. Well, how do I know it doesn't exist? Well, we're going to have to prove that, right? We can't just say that it doesn't exist. Maybe we just haven't found it yet. But I'm going to actually use a proof by contradiction to prove that this doesn't exist. And here's how we're going to do it. If you remember how to do proofs by contradiction, we're going to start by supposing that it does exist. Right, because we're going to start by supposing the negation of our original statement. Well, in order for it to exist, for a simple graph, to possess a node, or vertex with degree 4, well, what does that mean? That means that then 4 other nodes, it must connect and to 4 other nodes because it's simple. And since it's simple, those other nodes also need to be distinct. So what we have is if we have an edge or a vertex of degree 4, it needs to connect to exactly 4 other edges or 4 other vertices. But what does that mean? Well, how many vertices are there? There's going to be 1, 2, 3, 4, 5. That means the graph must have at least 5 nodes in it. But there's our contradiction. And our contradiction is that we said this graph, as stated in the problem, which has only 4 nodes, we said a simple graph existed with those degrees, and it doesn't. So that's our contradiction. Therefore, so we said this graph cannot exist. Right? Just because we're dealing with graphs does not at all mean that we can't do proofs over them. Here's a proof by contradiction. We could do direct proofs. We could do proofs by induction. In fact, proofs by induction are a great way to prove things about graphs.